Hello everyone and welcome to my poster presentation. Today I'm going to present the first study, which is development of hysteresis-free and linear knitted strain sensors for smart textile applications. And I'm Beyza and I'm a PhD student at the Faculty of Industrial Design Engineering in TU Delft. And for the introduction, many smart functions can be integrated into the applications by benefiting from the intrinsic qualities of textiles, such as comfort, and among all, knitted strain sensors can possess a great benefit in terms of seamless integration. So that's why they can be used for health monitoring applications. And in this study, we would like to investigate the electromechanical performance of the knitted strain sensor. That's why we made a systematic study by varying the yarn material and knitted process parameters. And in the end, we found out a new way to manufacture a linear and hysteresis-free knitted strain sensors. For the samples, as you can see, we used the RIP 101 knit design. As you can see, the conductive and elastic yarn were inserted together at the sensing area. And for the electromechanical properties were evaluated in terms of different design parameters such as gauge factor, hysteresis, and working range. And for the first study, we evaluated the effect of fabric count and elastic yarn type on the performance of the sensor. As you can see, when we increase the fabric count, the gauge factor and working range systematically decreased. So the tighter structure results in a low sensing performance. And this was also observed for the different type of elastic yarn. And for the following studies, we used optimum yarn because of its high elastic recovery properties. And also we would like to investigate the effect of different type of conductive yarn on the performance, sensor performance. That's why we use different type of conductive yarns from two different group. From one of them is Shieldx, the other one Amman. For the Shieldx yarn, there was a trend. So at the lower initial resistance, the gauge factor were reported as higher, but this trend was not observed for the Amman group because of the yarn structure, hybrid yarn structure. The essential part here is the yarn configuration effect, conductive yarn configuration effect. So far all the samples were produced in which the conductive yarn was inserted at the R side, but for this case we changed its position from changing at the yarn carrier. As you can see, the black one represents the conductive yarn. In this way, the conductive yarn was inserted inside. And this was the result of conductive outside and conductive inside. So hysteresis value was drastically declined from 0.15 to 0.03, and as well as gauge factor increased from 0.70 to 1.19, and also the line became more linear. The working range was also gets wider when we change the yarn position. That can be explained with the contact points change of the overlapping yarns, which results in a resistance change. And as a conclusion, we can say that tighter structures results in a low sensor performance with low gauge factor and low working range. And also the positioning of the conductive yarn results in a drastic change in hysteresis values. So these hysteresis value, in the future work, this knitted strain sensor with low hysteresis value will be evaluated at actual wearing conditions. Thank you for listening.